Hello teacher, I'm Sun Carol and this is the video presentation for Team3 Linux vendor of CPU scheduling algorithm simulator. So this is a team of 4, me, Sun Carol, Rachan Kolabot, Theng Van Heng, and Lao Henrut. So here I will be doing the introduction and also the code explanation. The whole reason of this project is so that we can understand how to implement the CPU algorithm, and the technology that we use is Java using Maven project compiler. We also use Jackson data bind for the JSON serialization. Let's start with our project architecture. So first, our project start off at app, and these are where we read off the default value for each process. And this is saving process and reading process by using the JSON mapper by using the object called process. Process will have PID, arrival time, burst time, priority, and all these variables that are calculated value, and also two constructor. Moving on, we will go into the main menu where the process actually starts, which is from main scanner. We pass in a scanner object into an instance of menu. And so if we go into run, it will run this, and we use a enum class for conditioning which a menu should happen. And so what I'll do now is explaining how the simulation works. Let's say, for example, we go into MLFQ, which has a handler function or handle run MLFQ. So in MLFQ, we choose the default value of the queue to be 3, but we can also set to however many queue that we want. Next is we determine, what should a quantum value be? The quantum value is first predetermined as default as 2, 4, and 0 for first come first serve, which is stored into quantum, and then it is passed directly into the quantum LFQ algorithm. Before we go on to that, let's look at how it is run. It first checks the scheduler. We take the scheduler interface as MLFQ, and we upcast the MLFQ algorithm class, create a simulator object, and run the function by passing the current processes, which is read by the start of the program and also our algorithm scheduler. So if we were to go check into the MLFQ algorithm, we will see that this is the constructor. These are the variables, the quantum, the number of levels, and the double-ended queue. The add process will just append the process nucleus process into the highest level of priority, which is 0, to the end. And the next process is where it moves from one process to another. Current is the current process being run by the CPU. And we check that if it's not null. If it's not null, then we check that, is there a higher priority? If there's a higher priority, we will kick out the current process to null, and we check that, the level of the highest non-level function, which is a helper function. And we also check that if level is equal to -1, is not equal to -1, we set current to be a process stored inside one of the level of queue. The level of queue here is just choosing the highest current level, and then we will return the current from the next process. Moving on to the record tick function is where our MLFQ actually really works, is that we check if the process is currently in remaining time equals 0. If not, we continue. We increment the use at level. This is to keeping track of the quantum. And we take the quantum and we check that, is the tick use at level is bigger or equal to the quantum. If it is, that means that it exceeds its time. It will move on to the next level of the value variable of next level of queue, and also we add the current process into it. This is to say that, if the process ran already and it is over its quantum value, we will demote it to the next queue level. And then we reset or clear the CPU, what it is holding. This is just a remove process from the queue, and this is the helper function of highest non-level to check that, which queue is empty, and if which queue is empty, not empty actually, and see that which variable is storing, which process is storing that. Now let's go look at the CPU simulator, which is where the whole logic is encompassed, where it gets whether it deals with every algorithm like first come first serve or round robin, etc., etc. In this scenario, we call the run function we saw just now, and then we do a deep copy, meaning that we take every single process in the list and make an exact copy. We don't use the original because that will mutate it. So, and every other processes and every function cannot use it. Here, this is a list of completed, list of timeline, the CPU object, which if you go to look into here, it has the current process, idle, boolean, assign, and run. Run will decrement it by 1, assign will just set the process, and also if it's the process start time is equal to -1, meaning that it's not started at all, we set initialize it to time. Moving on, this is the main loop that runs the algorithm. So we run it for however many process we have, and then this is copied by taking the process at the first one of the scheduler and add it to the scheduler, meaning that we take the process from the copy at first index, and then we add it to scheduler. And then process next is just taking the schedule, taking the process from the scheduler, and then running these checkers. If the process is, this is to say that, oh, is the next process the same or not the same to the current process held by the CPU? If it's not the same, we do a variable of getting a GAN element next. And then we set the variable to CPU assign, and if not, we set CPU of current process equal to null. Active start is equal to time. This is basically to check, oh, when did the process start? And here is where we execute the run. So we take the process that we passed in just now, we run it, we decrement it by 1, we record the tick using the record tick so that, oh, we can do round robin and, no, not round robin, MLQ, meaning that there's multiple queue to record how many times it ran. And here is the checker for current process remaining time. If it's equal to 0, that means that it's finished. We do calculation of all the variable like finish time, turnaround time, waiting time, and also we complete add, remove from the scheduler, and also add it to the timeline with a GAN element. GAN element is just like I mentioned, is the start and end, is to record the start and end for the GAN chart. And then we increment time. After the loop is done, we will calculate the average of total waiting time, turnaround time, response time, and then we find the average and pass it into the object of simulation result. Deep copy, as I mentioned just now, is just one-to-one copy with the original process list. And in here, the simulation result is where we actually print out the table of the processes, their start time, arrival time, end time, finish time. And also we store this variable and then we pass it. If we check where it is called, we pass it into a function called result printer. In here, one sec. In here is actually where we print all of the table of the result, which will be shown by Van Hein in the next section. And this is the algorithm comparison, meaning that we run every algorithm to compare. And this section is where we actually print the GAN chart. Basically, as you can see here, we take the GAN element list that we made along the way, and then we start building it. We start building it that which process start when, which process and where, and then it build the whole thing. So that is all for the introduction to our architecture. Next is Van Hein will do the live demonstration.
Okay, hello teacher. My name is Van Hein and I'm be in charge of the live demonstration. So let's start. So we're gonna first load our process, and we could see here the process ID and arrival time and burst time. We could also display it here again to see. And then we could select our algorithm. Like here we start with first come first serve. Here we see the simulation result where which process is which, and the arrival time, burst time, and starting time with other time, and we can see the average waiting time, turnaround time, and response time here. And this is the Gantt chart displaying which process runs. We could select other algorithm like SLT, we display the same thing, but how different algorithm is applied to each, even in the Gantt chart here. So even SGF, round robin. Oh wait, sorry, 5. We could here enter our quantum, so we could choose default 2. It will display all the times again and the Gantt chart, and amount of Q. We're gonna enter the level. It's also like default, and here you can see all the result again, even the Gantt chart. That is it for my demonstration.
Good evening, teacher. My name is Rachan Korbot. I will present the part where we have to analyze the average wait time, average turnaround time, and the average response time. Now, before we go forward, we will first, let's remember what it is first. First come, first serve, self-explanatory. The first process that come will take up first. First job first is after you finish a job, you will look for the next shortest job and will not change the process until it finished. Shortest remaining time first is when a new job comes in, you will check everyone's remaining time and do the shortest one first. And then when a new job comes in, it'll do it again. It won't wait for the jobs to finish. For round robin is we have a quantum time and we add every process into a queue, and every process will take up that amount of quantum time, pause, and go to the next process. Multi-level queue is you have multiple queue with multiple priority. Normally, the highest priority have the smallest quantum time. So it's like round robin, but with a lot of it with different quantum time and rules. Now, first, we will look at the wait time. Now, normally, if you have short wait time, you would also have short turnaround time, and the shortest one is the shortest remaining time. Now, these three up here would have shorter wait time, but in worst case scenario, the shortest job first and the first come first serve is if the first job have a large burst time, then these two would actually have the worst average time as well. But no matter, shortest remaining time first will always win mathematically, because let's say if you have 1,000 process, and if 900 of them are short, then it will clear the 900 first, no matter its arrival time, and the last 100 will get cleared last. Because we clear the 900 first, the average waiting time will come down. Now, shortest job first will also do something similar, only in the case that it gets the largest job at the start, that it will run into the convoy problem along with the first come first serve. Now, the round robin and the multi-level feedback queue would not have a high average time, because it will only run for a fixed quantum time and it will move on to the next process. So no matter if the process is short or long, if the process is short, it will have to wait for an entire queue, if it's just slightly bigger than the quantum time. So that's why the average wait time for the shortest remaining job first is always low. And for the next one is the average response time. Now, the average response time is the amount of time where the process arrive and then the process get worked on. While the reason why I have big wait time and small response time was, sure, it arrived and then it get worked on fast, but it moved on from that process just as fast. That's why, like I said, for this is it arrive fast. It takes a bit more to respond to, but it get the job done fast. Because it doesn't just change, it only do the remaining time, the shortest remaining time first. Okay. So you know the concept. Now, the reason why multi-level feedback is even better than round robin is because it has the highest priority. When a process goes to a lower priority and a new process comes in, the priority will take precedence for the new process. So whatever we do, we stop for now and we run the new process. That's why it's low. Now you see 1.5 because we only have a small amount of process. If you have more process, you will see that it could even get shorter. Okay. And also multi-level feedback queue guarantees that the process would not starve. Now this looks good, the number look good for average wait time and average turnaround time, but because it keeps doing the shortest job or shortest remaining time first, the longer one would always starve. But this one, it doesn't, because let's say we have two level of queue. To make it simple, one queue, it has a quantum time, and the second queue doesn't have a quantum time. So when we do the first queue, let's say 5 quantum time, you do it, and then it moves to the second queue. It will finish that second queue, then it will move on to the next element of the second queue. But because there's a priority, the short one will be done. If it's smaller than the quantum time, there's practically no waiting time at all. But we always have the second queue, which is like running in background, so it won't get starved. And in practice, we use multi-level feedback queue because we really don't know how long the job lasts. We also have to know how long the job lasts. We also have to spend a computing time to figure it out. So this is actually not the best one because we don't know how long it lasts. But it's the best on paper, and this is the best in practice. Thank you. For the next part, Hedrat will be the one explaining.
So during our development, we had met with some challenges, and first one was deciding on what coding language and what build tools we should use. So during our choices, we had JavaScript. It is all around platform compatibility. As long as one can run a browser, they can run the program. But some of us don't have that much experience with JavaScript. And the other choice we had was C++. So C++, it's easy to hold a project because you can just include other files and you don't have to have all those confusing build tools. And for Java, it has the bunch of build tools. It's hard to set up the environment properly, but it will be easy after we set it up. So during our conversation, we land on our choice, which is Java, because it was chosen for the OOP focused approach, and we chose Maven as our build tool. So we can call the jar file from online from the POM XML file, so we can talk with the JSON files. So during the file, we want to store our examples of the arrival time, the individual process. So we thought about the CSV and JSON. So the CSV, by far, it was easy and it should be the practical one, but we thinking maybe we should use JSON if we want to learn. And the problem was the file IO JSON was new to us, so we had to research how to structure the JSON file correctly and also figure out how to load into our program. And the solution was from up here that I mentioned. We call it from like an online jar inside our program. Using the Jackson data bind library allow us to store the process list inside the structured format, which in our program, which is the process.json. This structure makes it easy to load into our Java program. And now for the big one, which is the tick-by-tick CPU simulation engine. So we have to simulate how the CPU works. So the problem was the CPU sketching in code requires simulating individual ticks. The main issue was coordinating the arrival time of every individual process, and especially for the preemptive ones. So we have to prioritize which one runs first, the decision, the steps, and then the context switching, and then doing the same tick without being off and causing a lot of mismatch. So the solution is we implemented by part. So we have first we check for arrivals. This will be the priority. Which one run first? So first check new arrival, add them to the scheduler, create the scheduler for the next process. So scheduler in here in the program, it means the different algorithm. So it should be the first come first serve, round robin, etc. Is scheduler means the algorithm that we use. Create the algorithm for the next process. Compare the next process with the active process to detect a context switch. So we can save it and then lock it into the Gantt interval. So we can create the Gantt chart. So we execute the process for one tick and then we loop everything again. And then we decrement the remaining time for the process. And finally, we increment the global time clock. So for the Gantt chart, since different process will run at different times depending on what the algorithm that we use. So we could have the round robin, which splits down a lot. So we have to format it correctly so that it will look nice inside the CLI. So the problem, we break down the process into tiny blocks and then just save them every time. And then the solution is we use a list of Gantt element objects storing the process ID, the slot time, end time to build the timeline, and then a printer utility to scale the blocks with the width align boundary and numbers dynamically. This just means that the Gantt chart would be dynamic width as long as the list of process that it got fed by the context switching is correct. So in our conclusion, by building the CPU simulator, we learn how the CPU works by looking at our code, and we have implemented to simulate a CPU, and we're able to implement algorithms like the first come first serve, shortest remaining time, shortest job first, round robin, and MLFQ. So we got valuable insights on how the logic itself works rather than being shown how it works in class by looking at the code and then making it ourselves. And also we're able to learn how to use the JSON file by like writing out and also writing into our program, loading into our program. We learn finally the trade-off that we have, which is the difference between the first come first serve and then the MLFQ, is that the first algorithm is way more simpler than the first one. But being simpler means that it is not adaptable and it can run into problems such as giving a shorter time run, causing the convoy effect, causing poor response. And then the second algorithm, it is modern, complex, and computing adjusts its limitation dynamically by adjusting the process priority based on the execution history, giving a higher throughput and responsiveness. And that will be all for our project.